section 4.1, part 2, and it's pretty much going to cover the very last 3 slides of the packet. So last class, and this was being recorded during 7th period. Last class, we were able to finish this slide, however, we were rushing, so I'm going to go over it again. What we're going to do, we were using this formula back at the beginning of the section to calculate the angle measurement. And so to do that, we were taking the arc length and then dividing it by the radius. And we did a couple of examples where we were calculating, for example, here we had R, and then we were calculating, okay, so the arc length will be, the angle measurement using this formula will be S, it's for arc length, so the arc length is 2R's divided by the radius, which it just happens to be R. And then from here we were getting, okay, this angle, the central angle is actually equal to 2 radians. We also used that formula to figure out what was the whole circumference in terms of radians, the central angle. And so we used that the arc length of a circle, or the whole circumference, was 2 pi r. You've been using this formula since elementary, right? To find the circumference of a circle. And divided by the radius, so that's how we discover that the angle for a whole circle, the central angle, like from here to here, will be 2 pi. We knew that it was 360 degrees, but we didn't know it was 2 pi. All right, that was just a little review. Now, what we're going to do from here, well, I think you guys did it already. We solved for S, right? And so we know R is dividing S right here. And so if we solve for S, we will have to take this R, move it across, and so it will be multiplying theta. So S is equal to R times theta. And I believe I told you to make sure that your angle is in radians, correct? I told you that? Angle must be in radians. So when you are studying for your test, you know, make sure you pay attention to that. The angle needs to be in radians. If it's not in radians, you're going to get the wrong answer. All right, now the problem at the bottom of the slide, we're going to use that formula to find the arc length, and that will be the radius times the angle. The radius is here, it says it's 10 inches, and the length of the intercepted arc is, we need to find the length of the intercepted arc, and we are given that the central angle is 120 degrees. Okay, so first we need to convert the angle, which is 120 degrees, to radians. So we want to have the unit conversion factor that has pi on top. So if we do that, degrees, they cancel. Here we have radians for units. So we will have 120 pi divided by 180, right? And then after dividing, I believe we divided by 60. So we got 2 pi over 3. Yes? Is that correct? Okay. And so what we did right after that, then we were able to use the formula, this formula here. And so we have that the arc length will be the radius, which is 10 inches, times the angle, which is in radians, 2 pi over 3. So here we will have 20 pi over 3, and this is in inches. Because we are talking about length, so we need to have a unit that it is for linear quantities, such as inches. All right. Now, let me ask you guys something. If I was to have 2 circles, let's say a small one and a big one. And so 120 degrees is going to be maybe somewhere here. So let me ask you guys, if the central angle is the same, 120 degrees, will the arc length be the same? No, it will not, right? So I see most of you shaking your heads. No, it's not. So someone who said no would like to say why? Anyone? A lot of you are shaking your heads.
Because the radius isn't the same.
The radius isn't the same. So which one will be bigger?
The one on the right.
The one on the right. It's pretty obvious, right? That if we were to stretch this piece, you know, as a line, if this will be way longer. So this arc length is longer than this one. So that's why the radius actually matters. Let's say this was 10 and this was r equals 2. Okay, so for arc length, that does matter. And why do I say that? Because that actually has a lot of meaning when we solve the problems that we're going to see on the last 2 slides. So any question about this problem right now? You guys already have this answer, right? Yes? Okay, so let's go to the next one. Now, there are 2 types of angular speed. I'm sorry, of speed when we talk about rotations. And so one of them, it will be the angular speed. We're going to talk about that one first. So that one, it tells you how fast are you covering a certain amount of degrees. All right? So if we were to compare my 2 circles from here, let me give you a better example. Okay, so this is portraying a carousel, seen from top. Yeah, with the horses? Okay, all right, so let's see. Raquel, this is Raquel. And then here we'll have Adelina. And then let's get one of the guys. Miguel. Oh, okay. All right. And here's Peru. Okay. All right. And so they're riding the carousel, right? They're having fun. We're having fun. And so if we were to discuss the angular speed of Raquel, of Adelina, of Miguel, and Peru, that they will all 4 of them will have the same angular speed. They will all be covering a certain amount of degrees per minute or per second, all right? But if we talk about linear speed, who will have, let's say, who will be moving faster?
Peru.
No, actually, Peru will be the one moving faster. And he's going to have to do that to keep up with Raquel. Raquel will, well, not Raquel, but Raquel's horse will be the one moving slower, right? Okay. So let's look at the formulas, and then we'll go back to that problem. So for angular speed, we will use this letter, which is actually omega, another Greek letter. More specifically, it's lowercase omega. There's an uppercase. Huh? The baby omega. I know Miss Tabor calls it that, baby omega. Yes, it kind of looks like a chunky W.
Like a Walt Disney W.
Yeah, kind of. Yes. And so, to do that, of course, the formula is the degrees, or the radians, divided by time. All right. Now, to look at the linear speed, I want you guys to do the following. So this S, I want you to substitute it with the formula for arc length, which is right here. So you should have something like, instead of S, we will have R theta over T, just like that. That's all I did. I just changed the S for R theta. And now what I want to do is factor out the R. Okay. So according to this second formula right here, what does theta over T equals to? Omega, right? Or the angular speed. So what this means is that the linear speed could be found by multiplying the radius times the angular speed. Let me write it on the right side so it makes more sense. So r times angular speed. Because that's what it means. So depending on how big the radius is, that's what the linear speed will be. All right? And last year, if we have time, I'll take you guys outside and we'll do a rotation around the flag. So you can see. Last year I put myself at the end. This year I'm going to put myself at the center. Okay, so let's answer this question here and then we'll move to the last one. So we have a hard drive in a computer that rotates at 3,600 revolutions per minute. Remember, one revolution is a complete turn, right? How many radians are in each turn?
2.
2 what? 2 pi. So if we want to know how many radians are in 3,600 revolutions, what should we do? Multiply by 2. Multiply by 2 pi, yes. So we have that one revolution is equal to 2 pi radians. So the unit conversion factors will be either 1 revolution over 2 pi radians, or, and you can use the system for physics in Excel, 2 pi radians over 1 revolution. So since we have 3,600 revolutions in 1 minute, and we want to convert this to, let me see, express the angular speed of a hard drive in radians per minute. So we're going to multiply by which unit conversion factor? 1 or 2? 2, right? Because we want to cancel revolutions. And you guys already told me, you just multiply by 2 pi. So we cancel revolutions. And we have 3,600. Oh, I'm sorry, not 3,600. What is 2 times 3,600? Oh, what? Okay. 7,200 pi radians per minute. So the disk, the hard drive, is rotating at 36 revolutions per minute. Translated into radians, that means 7,200 pi radians per minute. What would we do if we want to convert this to seconds?
Multiply times 60.
Divide by 60.
Yeah.
Should we multiply?
Divide by 60.
So think of this. Do you want to cancel minutes, right? So where do you want to have minutes? On top or the bottom? On top. 1 minute is how many seconds?
60.
So then you will actually divide, right? So of course, if we divide 7,200 divided by 60, I should be able to do that, right? 120. Oh, thanks. So 120 pi radians per second. This way to do conversions, it might come in handy, especially if you have to take engineering physics, because you're going to convert for units, like several units all at once. So if you just keep using those fractions, it's pretty easy. Yes? Question? All right. So is it clear how to find the angular speed? We haven't even, well, yeah, this is angular speed. The angle divided by the time. Now let's talk about linear speed. And so as we already went over, linear speed will be the product of the angular speed times the radius. So the bigger the radius, like in the case of Peru's horse, right? faster. It had to go faster to keep up. All right, so we have a wind machine used to generate electricity. Shocking. Has blades that are 10 feet in length. What? I say shocking that it generates electricity. What? So 10 feet in length. You guys know that we can also get electricity from the sun? Have you guys heard that? Okay, I'm glad. All right, so to generate electricity, it has the blades that are 10 feet in length. So we're going to consider that to be our radius. Okay, so the radius is 10 feet.
Are those blades huge?
They are huge. Have you ever seen them?
Yeah.
Like on the road?
Yeah.
Like when they're being transported? It's ridiculous. Yeah. Like imagine if one of those falls.
Why would you imagine that?
Well, because we were using this for a whole field of them.
Well, we would have to take a short break. Yeah? Okay, so let's hurry up. All right, so we have here, the question is to find the propeller is rotating at 4 revolutions per minute, right? I'm sorry, per second. So every second, they're doing 4 turns, right? So, find the linear speed. Before we can find the linear speed, we have to find the angular speed. So we have it in revolutions per minute. However, we want it in, what is it called? Radians per minute, right? Okay. You already did time, Simon started with the unit circle. Okay, so the angular speed is going to be 4 revolutions per 1 second, sorry. And so we're going to convert that. We still want our linear speed per second, so we don't need to worry about the time. But we need to convert the revolutions. 1 revolution is equal to 2 pi radians. Okay, so in this case, we will have 8 pi radians per second. Or 8 pi radians divided by 1 second. Okay, now I'm going to go back over here, and I know that for the linear speed, I need the radius times the angular speed. And I can assure you that you will have a problem like this in the test, like, I promise you. So, test question. Okay, you make sure you do master one of those problems. So here, the radius was 10 feet. The angular speed is right here. It's pretty easy. 8 pi radians over seconds. And so the linear velocity will be 80 pi feet per second. To be honest, I don't know how they get rid of the radians. I try to look on the book. It didn't really make sense to me, so we will just say by magic. All right, so let's go outside. We'll do that rotation quickly, and then we'll come back and get started with 4.2, okay? All right. Chris, grab one of the unit circles for yourself. Oh, of course you did.
Oh, no. I told us to get.
Yeah, Karina told me to.
Oh, I'm still recording. Okay, if you need to use the restroom, go now, and then we'll meet by the flagpole.